Hello everyone. Hello guys. I hope आप सब लोग अच्छे होंगे. So please tell me, is audio video clear? Tell me guys. I think audio video is clear. Okay. So in today's session we'll revise the phase control rectifier, especially single phase control rectifier. So we will revise this chapter. So please share today's session to everyone so that everybody can watch this session, and because this session is purely on revision based, and I'm not going to tell you about the basic things because you already know the basics things. So what I will tell you is the main important things which you are lagging, or maybe the point which you need to remember, or you can say you need to consider those points, because otherwise you will make mistakes in the question. And so those points I'll discuss in today's class, and I'll take some questions also. I'll give you some homework questions also. So we will discuss that part. Okay. So I think it's time to start. So let's start the session, guys. This is my introduction. Those who don't know me, I'll teach almost every subject. So right now I'm teaching power electronics. After that, machines will start from maybe 17th or 19th, I don't know, but the next subject will be electrical machines. So in electrical machines also I'll focus on induction part and synchronous part. Okay, so I'll consider that part, because transformer is again very easy. So I will take synchronous machine and induction machine. But before that, if you have not subscribed our channel, please subscribe it and like the session and press the bell icon so that you get the notifications whenever the session is live. This series is GATE AIMER'S series, and I hope you are enjoying well. So please do watch the other sessions also, the sessions of different subjects. You can watch these sessions under this series. And those who are preparing for GATE 2024, or if you are not preparing but your friend is preparing or your junior is preparing, please do tell him and tell him about this session, because there is one mega workshop is going on 18th of December. And in that workshop, Rakesh Talreja will give you some tips, and you will be benefited for that. Okay, so please tell your friend. There is one more series which is going to start, and in that series we will discuss about the PYQs of last 5 years. So we'll discuss that, and that series is going to start from like 18th of December. So again, I'm taking power electronics and machines and network theory. So you can join this series. You can watch this series live, and you can ask your doubts. Okay, so let's start the session, guys. But let me tell you, it's time for the test series. So you have to start giving the test series. Even if you have completed like 6 or 7 subjects, don't worry. Please try to give the mock test or the test series of that particular subjects, because whichever you have completed, please try to give the test of that subject, because the test series will tell you about your mistakes, about your speed, and about your accuracy. So it's very important to give the test series, and it's a proper time. It's a right time to give the test series, and BYJU'S Exam Prep will provide you the test series. So you can join the test series. In that test series, you'll get many tests, like 60 tests are there. And the tests are subject wise tests are also there, and the mock tests are also there. So you can give those tests. Okay, there is one All India Open Mega Mock Test for GATE 2023, and that will be, I mean, you can register for that from 13th December to 20th December. Okay, so the link is provided to you in the description, so you can register from that link. So let's start the session, guys. Now it's time to start the session. So the first thing is, in phase controlled rectifier, what we have is, first of all, I'm discussing about the single phase controlled rectifier. The first thing is RL load. If you know the analysis of RL load, using RL load, you can comment on R load and L load. Okay, if you know the RL load analysis, then you can comment on L load and R load. Okay, let's see how. First of all, we have RL load in phase controlled rectifier. So in RL load, we know that the conduction can be continuous, discontinuous, or just continuous. This current I naught T will be continuous, just continuous, or discontinuous. You should know the boundary. If you know the boundary, then you can also comment for R load, L load, pure R load and pure L load. Okay, let's see what is that boundary. Everybody, I think at this particular instant, I think you should know what is the boundary condition. At what firing angle the conduction current I naught T will be just continuous. And you can tell me about that firing angle. So that firing angle alpha is theta z. Whenever this alpha, firing angle alpha is equal to theta z, then you can say that the conduction is just continuous. Just continuous conduction will be there. Just continuous conduction. Now, if alpha is less than theta z, alpha is less than theta z, the conduction will be discontinuous. Conduction will be continuous. If alpha is less than theta z, the conduction will be continuous. Continuous conduction. And if alpha is greater than theta z, conduction will be discontinuous. Discontinuous. You just remember this point. So alpha will decide. If alpha is theta z, conduction will be just continuous. If alpha is less than theta z, conduction will be continuous. And if alpha is greater than theta z, what is this theta z? Theta z is equal to tan inverse of omega L by R. Omega L by R. Okay. So this is the boundary condition. Now, let's say the conduction is just continuous or continuous. In just continuous or continuous conduction, if you look at the output voltage average, V naught T average, that will be equal to 2 Vm by pi cos alpha. This formula is applicable because whenever the conduction is continuous, you remember in single phase, this will be the average output voltage. Just remember it. Okay. If you don't remember it, you have to draw the wave shape and then you have to calculate the average value. But if you remember it, you can directly use this formula. Okay. So if you have done enough practice, then I think you must know this. 2 Vm by pi cos alpha for just continuous and continuous conduction. I mean, if alpha is up to theta z, you can apply this formula. But if alpha is greater than theta z, then the conduction will be discontinuous and this formula will not be applicable now. Now this formula is not applicable for discontinuous conduction. Now for discontinuous conduction, you have some extinction angle. You have some extinction angle beta, which you need to calculate, and it's difficult to calculate. You can't calculate that angle. Okay, so that's why I'm not interested in discontinuous conduction mode, but I mean, you should revise your discontinuous conduction also, because there might be some question in which the conduction, it is given, beta is already provided to you and you need to calculate the average output voltage. Okay, so in discontinuous conduction, this will not be the average output voltage. What will be the average output voltage in discontinuous conduction? Let me write. So in discontinuous conduction, the average output voltage will be, that will be equal to 1 upon pi. Pi will be the period. 1 upon pi integration alpha to beta. Beta is measured from origin. Remember this. Alpha is also measured from origin. Alpha to beta Vm sine of omega t d omega t. Just calculate this. This will be the average output voltage. Okay, this will be the average output voltage, and this is the condition for boundary. So this is for RL load. So in RL load, we know everything about continuous conduction and discontinuous conduction, and for what alpha, what firing angle alpha, the conduction will be continuous, and for what it will be discontinuous. Now let's take some question. Let me frame some questions. Okay, let me frame some question. Let's say I have this again RL load. I have this RL load. So I have this RL load. Okay, and I have this single phase controlled rectifier. I have a single phase controlled rectifier. Okay, and I have an AC source Vm sin omega t. Okay, now it is given that alpha for thyristor, alpha T1, T2, T3, T4, alpha is 60 degree. This is variable R, and let's say omega is given as, this is Vm sin omega t, fundamental frequency is, let's say 100 pi radian per second, and L is given as 0.05 Henry. what is the maximum value of R? Find maximum value of R. Find maximum value of R for which conduction remain continuous. Conduction or I naught T remains continuous. This I naught T remains continuous. Conduction remains continuous. We need to calculate for what value of R the conduction remains continuous. Alpha is fixed now. Please tell me, guys, what should be the answer? You need to tell me the answer in ohms. What should be the resistance? What should be the maximum value of resistance so that the conduction remains continuous? Tell me, guys. Tell me, everyone. Tell me what should be the value of R for which the conduction remains continuous. Now alpha is fixed. Omega is 100 pi. L is given as 0.05 Henry. Please tell me what should be the maximum value of R for which the conduction remains continuous. Okay, let's see. We know that alpha is fixed and we want that up to 60 degree conduction should remain constant. Now, we know that if I increase the value of R, what will happen? Theta Z. Theta Z is tan inverse of omega L by R. Omega is 100 pi, L is 0.05. So if I multiply it, it will become 5 pi by R. Okay? This is my theta Z. This is my theta Z. Tan inverse of omega L by R. So omega 100 pi into L 0.05. So it will become 5 pi upon R. This is my theta Z. We know that if R is 0, then theta Z becomes 90 degree. It means if R is 0, then the boundary point, the alpha at which the conduction is just continuous, is 90 degree. If alpha is beyond 90 degree, conduction will become discontinuous. It means this is the boundary point if R is 0. Now, if I keep on increasing R, if R is increased, obviously this theta Z will try to decrease. This theta Z will decrease. If R is increased, then theta Z will decrease. I want that at alpha equal to 60 degree, the conduction becomes just continuous. Okay? So it means I want theta Z equal to 60 degree. If theta Z is 60 degree, then this is the boundary. At alpha equal to 60 degree, conduction will become discontinuous. If you further increase the value of R, the theta Z will become less than 60 degree. It means at 60 degree, conduction will become discontinuous. Okay? I don't know how many of you have understood this point. It is very important. Okay? So you can say that at theta Z equal to 60 degree, alpha is also 60 degree. This is the boundary condition. So what you can do is you can calculate tan inverse of 5 pi by R equal to 60 degree. So from here 5 pi by R equal to tan 60 degree, and tan 60 degree is root 3. So from this relation I can say that R is equal to 5 pi by root 3 ohm. This is the resistance value, guys. This is the resistance value. And this is the maximum resistance. If you further increase the value of R from this value, then this theta Z will decrease. This theta Z will be less than 60 degree. It means if alpha is greater than that value, conduction will become discontinuous. But I want that at 60 degree, conduction should remain continuous or just continuous in the worst case. So what I did is I applied the condition for the just continuous case. So this is the maximum resistance. This is the maximum resistance up to which the conduction will remain continuous. Is it fine, guys? I think this question was easy. Okay? I hope you understood it. Now let's come back. Let's come to this point. Now let me tell you some other points. So in RL load, I told you if alpha is theta Z, the conduction will be just continuous. If alpha is less than theta Z, conduction will remain continuous, and if alpha is greater than theta Z, conduction will become discontinuous. Now let's say alpha is greater than if I say that alpha is greater than 90 degree in RL load, if I say that alpha is greater than 90 degree, for sure conduction will always be discontinuous for any value of L. Whatever L you want to take, you can take any value of L. If alpha is greater than 90 degree, conduction will always be discontinuous. Conduction will be discontinuous. Conduction will be discontinuous. Okay. Let me repeat it again. I told you, if alpha is greater than 90, whatever value for L you take, you can take L up to infinite, no problem. If alpha is greater than 90 degree, conduction will always be discontinuous. Why? Because we know that, what is the maximum value of theta z? Can you tell me? What is the maximum value of theta z? The maximum value of theta z is 90 degree. If it is infinite, let's say R is infinite, or let's say L is infinite or R is 0, then the maximum value of theta z is 90 degree. It means up to 90 degree, in the worst case, up to 90 degree conduction will remain continuous. But if alpha is greater than 90 degree, whatever L you take, it will always remain discontinuous. So remember this point, because this is very crucial point, guys. Don't try to forget it. Okay, so it's very important. Now I also told you via this question, using this question, I told you that if alpha is fixed and if you are varying the value of R, then also the conduction may become discontinuous. So if alpha is fixed, R is variable, again conduction can be continuous or discontinuous. R will decide the conduction. R will decide the conduction whether it is continuous or discontinuous. Similarly, if R is constant, alpha is constant, L is variable, then also you can calculate the critical value of L, for which the conduction will remain continuous and for which the conduction will become discontinuous. Okay, so there are so many type of questions you can frame from here. Okay, now let's come to other type of load. It's not necessary that the load is RL. It might be possible that load is R only. Now if load is R only, then theta z will be 0. Let's say the load is purely resistive. Let's say the load is purely resistive. If the load is purely resistive, if L is 0, let me write the next point. If L is 0, L0 means purely resistive load, then theta z will be equal to 0. It means conduction will be just continuous only for alpha equal to 0. If alpha is greater than 0 degree, then conduction will become discontinuous. It means in R load, in resistive load, if L is 0, you can put L0 here in this equation and you will get theta z equal to 0. So if you can say that the load is purely resistive, then the conduction will always be discontinuous except alpha equal to 0. Because at alpha equal to 0, conduction will become just continuous. If L is 0, then theta z will be equal to 0, and I can say that alpha 0 represent just continuous conduction. Just continuous conduction in R load. Just continuous conduction in R load. If L is 0, it means the load is purely resistive. In purely resistive load, theta z is 0. It means if alpha is 0, then the conduction is just continuous. If alpha is greater than 0, then the conduction will be discontinuous and alpha cannot be less than 0. Okay, so in R load, either just continuous conduction is there or discontinuous conduction is there in pure R load. Now let's come to pure L load. So if R is 0, R0 means pure L load. If there is pure L load, then I can say that theta z will be 90 degree because R is 0. You can put R0 here. So you can say that theta z is 90 degree. It means if alpha is 90 degree, conduction will be just continuous. Okay. If theta z is 90 degree, you can say from here, you can say that if alpha is 90 degree, conduction is just continuous. And periodic. Current will be just continuous and periodic, I not T. If alpha is less than 90 degree, conduction will be continuous. If alpha is less than 90 degree, in this situation, in this case, if alpha is less than 90 degree, you can say that conduction is continuous. Conduction is continuous. Conduction is continuous, and you can say that V naught T average will be equal to 2 Vm by pi cos alpha. Since alpha is less than 90 degree, it will be positive. So you can say that across this pure inductor, if R is 0, the load is purely inductive. Across this pure inductor, average voltage is positive. It means current will be continuous and rising. Current will be continuous and rising. Current will be continuous and rising. This rising word I have written later, just after this. Okay, because I know that average voltage is positive. Alpha is less than 90 degree, then the conduction will be continuous. We know that from this condition, from this theta z condition. If alpha is less than 90 degree, conduction will be continuous. Continuous conduction means this will be the average output voltage, and for alpha less than 90 degree, average output voltage is positive. It means the voltage across the inductor is positive. Average voltage across the inductor is positive. If the average voltage across inductor is positive, current will keep on rising. It will be continuous, but it will be aperiodic. It will be rising. Okay, now if alpha is greater than 90, if alpha is greater than 90, conduction will be discontinuous. In pure L load, conduction will be discontinuous. Conduction will be discontinuous. And in discontinuous conduction, in pure L load, if the conduction is discontinuous, if the current is discontinuous, it must be periodic. Remember, in discontinuous conduction, current will always be periodic. Whatever type of load is there. Whatever type of load is there, if conduction is discontinuous, it will always be periodic. It means I naught T will be periodic. Conduction will be discontinuous and periodic. Current will be periodic. Across this L, through this L, current will be periodic. Now, if the current through the inductor is periodic, then you can say that average voltage across inductor will be 0. So now the average output voltage, now V naught T average will be 0. Okay, I don't know how many of you have understood this, because this is again very interesting case. This is again very interesting. You should remember it. Okay, you should remember it. Is it fine, guys? Can I proceed? Tell me, everyone. I hope you understood it. So using RL load, you can comment on pure L load, pure R load. You can see that this condition I have applied for pure R load. This is pure R load. And then I take R equal to 0. It means pure L load. So this condition is for pure L load. After this line, I have written this line. So you can comment on every type of load, pure R load, pure L load, pure RL load. Okay, using this condition. If you know the condition of RL load, then you can easily comment on other type of load. Now let's come to the next point. And let me tell you guys, if alpha is fixed, L is fixed, and R is variable, then R will decide the conduction, whether it is continuous or discontinuous. If alpha is fixed, R is fixed, then L will decide. There will be critical value of L also, okay, for which the conduction will become continuous and discontinuous, okay. Similarly, if RL is fixed and alpha is variable, then also you can calculate the value of alpha for which the conduction is continuous or discontinuous, okay. So this is very interesting case. This is very interesting case, and this is very interesting question, okay. Now let's come to the RLE load. Let's come to RLE load. Now I have RLE load. Now again in RLE load, the E came into picture. It means again there are three type of cases. One is continuous conduction, the next is discontinuous conduction, and the next is just continuous conduction. So there will be some alpha for which the conduction will be just continuous. Let's say that alpha is alpha JC. For alpha equal to alpha JC, JC means just continuous. For alpha equal to alpha JC, you can calculate that alpha JC. It's very easy. Okay, I'm not telling you how to calculate that, because in my other lectures I have already told you how to calculate this alpha JC, for which the conduction remains just continuous. So in RLE load, you can calculate the value of alpha for which this current remains just continuous. Okay, so you can say that alpha equal to alpha JC, for alpha equal to alpha JC, conduction will be just continuous. Conduction will be just continuous. Conduction will be just continuous. You can calculate that alpha JC. I'll tell you how. I'll tell you how to calculate that alpha JC. So for alpha equal to alpha JC, now it is not theta Z this time, because in the previous case, that alpha equal to theta Z. If alpha equal to theta Z, the conduction will be just continuous. But now in this case, that alpha JC will be less than theta Z. Okay, we have to calculate that alpha JC. I'll tell you how to calculate this alpha JC. I'll tell you. So for alpha equal to alpha JC, conduction will be just continuous. If alpha is less than alpha JC, conduction will be continuous. Conduction will be continuous. And for alpha greater than alpha JC, conduction will be discontinuous. Okay, it means you have to calculate this alpha JC. If you know this alpha JC, you can comment whether the conduction is continuous, discontinuous, or just continuous. Okay, so it's easy peasy. But remember, when the conduction is just continuous or continuous, average output voltage will be again 2 Vm by pi cos alpha. Okay, so you can say that it will be 2 Vm by pi cos alpha. This will be my average output voltage for continuous conduction or just continuous conduction. But in discontinuous conduction, average output voltage will be different. You can say the beta will come into picture, and then you have to apply the concept of extinction angle. And from using that concept, you can calculate the average output voltage. Let me write the expression for average output voltage. I don't know how many of you remember this. Average output voltage is 1 over pi, because the period will be pi. From alpha to beta, average output voltage will be like this. Now from beta to pi, output voltage will be E. This way you can calculate the average output voltage. I don't know how many of you remember this wave shape, because at this time, I mean, this is the peak time, you can say. So at this time you should remember, in RLE load, this will be the average output voltage. You can check it from the wave shape. Okay, and in continuous or discontinuous conduction, this will be the average output voltage. Now, what is this alpha JC and how to calculate this alpha JC? Let's say the question is, maybe there is some R and some L and some E is provided to you, and they ask you what is the value of alpha for which the conduction is just continuous. So we should know how to calculate that. Now how to calculate that, let me show you. We know that the load is RLE. Let me write the load. We know that the load is RLE, and let's assume that the conduction is continuous. If you can remember the formula for just continuous case, you can remember it. Otherwise, you just derive it. This is a single phase controlled rectifier. Okay, and now this is the supply. Let's say at alpha T1 T2 start conducting. This T1 and T2 start conducting at some angle, firing angle alpha. So at alpha T1 T2 start conducting, and at pi plus alpha T3 T4 start conducting. So whenever this T1 T2 start conducting, the current will start from 0 value itself, and I want that the current is just continuous. It means the current will again become 0 at pi plus alpha. Whenever this T3 T4 start conducting, just before that the current is again becoming 0, so that whenever they are fired, whenever T3 T4 are fired, again the current start building up. Then the current will be just continuous in that case. Okay, so what you need to do is you need to write the equation for the current. Let me write the wave shape for the, this is the supply voltage, we know that. This is the supply voltage, we know that. Now at alpha we have fired T1 T2, at pi plus alpha we have fired T3 T4. Now the output voltage will be, what will be the output voltage for just continuous case? The output voltage will be from alpha to pi plus alpha, the output voltage will be same as the supply voltage. And then from pi plus alpha to 2 pi plus alpha, since T3 T4 are conducting, the output voltage will be negative of the supply voltage. Whatever the supply voltage is, the negative of this will be the output voltage. I hope you understood it. Okay, so this will be the red line will be the output voltage. Now, what is the wave shape for current for just continuous conduction? For just continuous conduction, the current will start from 0 here, it will go to the maximum value, and then it will again become 0 at this point. Okay, it will become 0 at this point. This case is just continuous conduction case. So this alpha is equal to alpha JC. Now we need to calculate this alpha JC. We need to calculate this alpha JC. What is the alpha JC for which the conduction is just continuous and discontinuous, whatever? Okay, you can calculate that alpha JC. Now, how to calculate? We know that during this interval, T1, T2 are start conducting. It means the output voltage, this voltage is same as the supply voltage. So across this RLE, Vm sin omega t is applied. So the circuit will look like this. This RLE load is there. Across this RLE, the supply voltage is there. Vm sin omega t is there. This is Vm sin omega t. Vm sin omega t. Okay. Now the current will start flowing from 0 itself, because the initial current was 0. So you can say that the current will start from 0. Now I need to write the equation for the current. IT will be equal to Vm by Z. Let me write the equation directly. I don't know how many of you know how to write this equation. Minus theta Z, because this is important, guys. And I'm not going to tell you how to write this equation, because I'm already told you in some AC transient lecture, I have told you how to write this equation. So IT will be equal to Vm by Z sine of omega t minus theta Z minus Vm by Z sine of alpha minus theta Z e to the power minus r by omega L omega t minus alpha minus e by r into 1 minus e to the power minus r by omega L into omega t minus alpha. This is the equation for the current. And you can write this equation using AC transient. Now, if you have not understood the AC transient, then it will be difficult for you to write this equation. So please watch my lecture on AC transient, and then you can easily write this equation. So this is the current equation, guys, and this will start from 0. Now, for just continuous conduction, if alpha is alpha JC, then the current will again become 0 at pi plus alpha. Okay? It means what you can do is you can put this current equal to 0 and put omega t equal to pi plus alpha. At pi plus alpha, it should again become 0. Then only the current will be just continuous. So what you can do is, in this equation, at omega t, you put omega t equal to pi plus alpha. So if I put omega t equal to pi plus alpha, it will become Vm by Z sine of pi plus alpha minus theta Z minus Vm by Z sine of alpha minus theta Z e to the power minus r by omega L. In place of omega t, we have to put alpha plus pi. Alpha will be cancelled, so you'll have pi only, minus e by r into 1 minus e to the power minus r pi by omega L. If I put omega t equal to pi plus alpha, so this will be the current equation, and this has to be 0. This has to be 0 because the conduction is just continuous. In just continuous case, current has to be 0. We need to calculate alpha from this relation. What is this alpha? That alpha is known as alpha JC. That alpha is known as alpha JC. You can calculate that alpha JC. Let me calculate. So you can write 0 is equal to minus Vm by Z. It's very simple, guys. Minus Vm by Z sine of alpha minus theta Z minus Vm by Z sine of alpha minus theta Z e to the power minus r pi by omega L minus e by r into 1 minus e to the power minus r pi by omega L. Okay, and this is equal to 0. Now you can take this common and take on the left side. So if you take this common out and take on the left side, then you will get Vm by Z sine of alpha minus theta Z is equal to minus e by r into 1 minus e to the power minus r pi by omega L. So from this relation you can calculate alpha. Alpha is equal to theta Z plus sine inverse of Ez divided by r Vm into e to the power minus r pi by omega L minus 1 divided by, okay, if you take this common, you have the factor 1 plus e to the power minus r pi by omega L. Okay, you have one more factor because you are taking this side on this entire side on the right side, and you are taking this common. So you have taken this common, so this will be in the numerator, so you take it in the denominator. So you'll get e to the power minus r pi by omega L plus 1. So this way we can calculate this alpha. This is my alpha JC. This is my alpha JC. You can see that alpha JC is equal to theta Z plus this angle. This is the angle alpha for which the conduction is just continuous. If alpha is less than alpha JC, conduction will become continuous, and if alpha is greater than alpha JC, conduction will become discontinuous. Okay. Now, if you see it carefully, this is less than theta Z. Why? Because it is negative. Why it is negative? Because look, this value will be less than 1. So if it is less than 1, then the numerator will be negative. If it is negative, then you can say that the alpha will be less than theta Z. So this time alpha will be less than theta Z. Alpha JC will be less than theta Z. This time alpha will not be equal to this continuous conduction case. Alpha JC will not be equal to theta Z like previous case. In RL load, since E was 0, in RL load since E was 0, if you put E 0 here, then you get alpha JC equal to theta Z itself. So it means from this expression, you can also comment on the RL load. You just put E equal to 0. It will become RL load. And for RL load, this alpha JC, the just continuous case firing angle, alpha JC will be equal to theta Z only. But if you put E is non-zero, let's say, if E is non-zero, then you have to put this E value and alpha JC will be less than theta Z. Alpha JC will be less than theta Z. Is it fine? So this way we can calculate the firing angle for which the conduction is just continuous and discontinuous and continuous, okay, for RLE load. It's very important. Now let me tell you one more thing. For these two cases, let's say the conduction is continuous, especially if the conduction is continuous, for continuous conduction, alpha minimum is 0 and alpha maximum is pi minus sine inverse of E by Vm. I'm not going to tell you how this achieve. I have how I get this formula. Okay, this alpha max for continuous conduction, alpha min is 0, minimum alpha is 0, and the maximum alpha is 0. Maximum alpha is this. But let me tell you guys, up to this firing angle alpha max, up to this firing angle, conduction will not remain continuous. Conduction will become discontinuous just after this point, and then it will become discontinuous, and this is the maximum alpha up to which you can fire the thyristors. Similarly, for discontinuous conduction, alpha min is equal to sine inverse of E by Vm, and alpha max is equal to pi minus sine inverse of E by Vm. Okay, you can calculate like this. Alpha max is this for discontinuous conduction. This will be the alpha min and this will be alpha max. I'm not telling you how I have achieved this, so you just remember it if you don't know. And if you don't know it, please watch my lectures. I'll tell you in those lectures I have told you how I have received I have achieved these conditions. Okay, so I told you in RLE load. Now there is one more point in RLE load, and that point is if you reverse the polarity of E, then this quantity will become positive because this is negative. If you reverse the polarity of E, then I have to put E negative because here the E is positive. With this polarity I call it positive E. If I reverse it, it will become negative. Okay, so if it is negative and this is also negative, the overall quantity will become positive. Now you can see that alpha will be theta Z plus this quantity, and this will be positive again. So now the range of alpha JC can be increased if the polarity of E is reversed. So if the polarity of E can be reversed, then you can say that the range of this alpha JC can be increased. It might be possible that alpha JC comes out to be greater than 90 if E is reversed. If E is reversed, then it is possible that alpha JC become greater than 90 also. Now let's say I have reversed the polarity of E. And this alpha JC came out to be greater than 90. It means let's take a case. Let's say alpha JC came out to be 150 degree with this type of load RL, and I have changed the polarity of E. For this situation, if I reverse the polarity of E, the alpha JC came out to be 150 degree. It means up to 150 degree, conduction will remain continuous. After 150 degree, it will become discontinuous. Okay. Now remember one point. Now, if you put alpha equal to 120 degree, you know that the conduction is continuous, because if alpha JC is 150 degree and the firing angle is 120, let's say, since alpha is less than alpha JC, conduction will remain continuous. And in continuous conduction, this formula is valid. So you can say that the average output voltage now, is negative. Why it is negative? Because 2 Vm by pi cos alpha. This is my average output voltage, and alpha is greater than 90. So you can say that now the average output voltage is negative. But the current is only in this direction. Current cannot flow in reverse way. Current has to flow only in this direction, and this average output voltage came out to be negative if I have reversed the polarity E. If I have reversed the polarity of E, and if alpha is greater than 90 degree, then for continuous conduction, you'll get negative average output voltage. It means the average, the output voltage is negative. This polarity is negative. It means the actual polarity is opposite. The positive polarity is opposite. Now this, in this case, this load is delivering the power, because this current is entering into the negative and leaving from the positive. Now this load is delivering the power. Okay. So if I reverse the polarity, of E, then the power flow can be reversed if alpha is greater than 90 degree. Okay. If I reverse the polarity of E, and if I take alpha greater than 90 degree, then you can say that the power flow can be reversed. Power flow can be flown from the load side to the load source side. Okay. So this is again very important. This is very, very important. Okay. Ashok, sir, please take classes on problem solving on effect of source inductance. Okay. Okay. I'll take some classes on effect of source inductance. Already I have taken some classes. So Ashok, please watch those classes. Okay. So I told you about RLE load, guys. This is again very important, RLE load. Okay. So I have told you everything about RLE load, how to calculate this alpha JC, when this alpha JC will be less than 90 and when this alpha JC will be greater than 90. All depends on E. All depends on the polarity of E. If E is like this polarity, opposite to the current, if it's absorbing power, if this E is absorbing power, then alpha JC will be less than theta Z. If E is delivering the power, if E is of this polarity, then alpha JC will come out to be greater than 90 degree. Okay. It means you can increase alpha beyond 90. And if you increase alpha beyond 90, then this average output voltage will become negative for continuous conduction. Average output voltage will become negative. If the average output voltage is negative, it means it is delivering the power. So power can be delivered from the load side to the source side. Okay. I hope you understood it. So everything lies in equations. Equations are more important than politics. Okay. Now let's come to this case. Now I have this current source. Now in case of current source, we know that conduction will always remain continuous. There is no point of thinking about it. Okay. Now there is a current source. No? If there is a current source, current will always remain continuous. I naught T will always flow. So you can say that the conduction is always continuous. If the conduction is always continuous, output voltage V naught T average will always be 2 Vm by pi cos alpha. It will always be 2 Vm by pi cos alpha. Just remember this point. Output average will always be 2 Vm by pi cos alpha. Now, what is the maximum alpha you can take? Alpha max here is 180 degree. You can go up to 180 degree. Alpha max is 180 degree in this case. Okay, but in this situation, in RL load, what is the maximum alpha? In RL load, what is the maximum alpha, guys? What is the maximum alpha in RL load? Again, in RL load also, the maximum alpha is 180 degree. Alpha max is again 180 degree. But in that case, at 180 degree, conduction will become discontinuous and average output voltage cannot be negative. Here the average output voltage can never be negative. In RL load, average output voltage can never be negative. Just remember this point. In the worst case, it can be 0. But in this case, average output voltage will become negative. You can see that at alpha equal to 180 degree, it is maximum negative. It is maximum negative. Now you can question me, sir, but here also we can take alpha max equal to 180 degree. What's the problem? at alpha equal to 180 degree or more than theta z, this formula will not be applicable. Because according to this formula, if you put alpha equal to 180 degree, it comes out to be negative. But actually this formula is not valid for 180 degree. This formula is valid for 180 degree. Okay. And according to this formula, average output voltage will never be negative here. In RL load, average output voltage will never be negative. But in case of constant current source load, average output voltage can be negative if alpha is greater than 90 degree, and this formula is valid everywhere because conduction will remain always continuous. That's why this formula is applicable everywhere, and you can calculate average output voltage using this whatever alpha you take, you just put it here and you can get the average output voltage. I hope you understood it. Okay, and you can also draw the wave shape of the source current. Okay, I hope you understood it. So this is again important case. Average output voltage here can be positive, negative, both. And the source can absorb the power, it can deliver the power, depending on alpha. Okay, depending on alpha, it can absorb the power, it can deliver the power. I hope you understood it. Okay. So in current source, alpha max is 180 degree and average output voltage can be positive or negative. This formula is valid everywhere because conduction will remain always continuous. Okay. Now let's come to the next thing. Now I have this circuit. Let me change it. Let's take it diode. So it's a, you can say, now this is diode now. It's a semiconverter. So in case of semiconverter, there will be inbuilt freewheeling action. There will be inbuilt freewheeling action. Now you can see that these diodes D1 and D2, they don't require firing. They don't require firing. Let's assume that this is 0 and this is VST. Whenever, because these two diodes are under common anode configuration, they are under common anode configuration, the diode which has the lowest voltage at cathode will conduct. The diode which has the lowest voltage at cathode will conduct. So if I draw the input supply voltage, this is my input supply voltage, okay? This is my input supply voltage. Now I need to draw the output voltage, the wave shape of output voltage, okay? V naught T. I need to plot the V naught T. This is my VST. And the firing angle is alpha for T1 and pi plus alpha for T2. Let me take these points. This is firing angle alpha. Okay, this is pi. This is pi plus alpha. And this point is 2 pi. This is 2 pi plus alpha. Okay. Now let's see. We know that if VST is greater than 0, after 0 you can say that VST is greater, VST is positive. So you can say that D1 will conduct for sure. So during this interval 0 to alpha, diode D1 is conducting. D1 is conducting because this is positive, this is 0. The lowest voltage is 0. So the diode D1 will conduct. And T1 will start conducting after this point. It means which device is conducting. If T1 is not conducting, because T1 will start conducting after alpha, it means T2 is conducting. Is it fine? Is it fine, guys? Let me check. It means T2 is conducting. So you can say that during this 0 to alpha, in these two diodes, D1 is conducting. What about these two devices? T1 is not conducting because T1 will get the fire after alpha. So you can say that between 0 and alpha, T2 will be conducting. So now the current is freewheeling. Current is freewheeling. So you can say that D1 and T2 are conducting. So you can say that current is freewheeling. Output is 0. From 0 to alpha, output will remain 0. Current is freewheeling. There is an inbuilt freewheeling action. Now what will happen after alpha? After alpha, again, VST is positive. VST is positive up to pi. Up to pi, you can see that VST is positive. If VST is positive, then this D1 will conduct because it has the lowest voltage on its cathode. So D1 will conduct for sure. And we have fire T1 here. If you have fire T1, obviously T2 will get reverse biased and it will be turned off. Now D1 and T1 are conducting. Now D1, T1 are conducting. If D1, T1 are conducting, then the output voltage will be same as the supply voltage. This point is sorted here and this point is sorted here. So you can say that the output voltage will be same as the supply voltage. So now from this point onward, the output voltage will be same as the supply voltage up to pi. Now what will happen after pi? T2 will start conducting at pi plus alpha. At this instant T2 will start conducting, but before that T1 is conducting for sure. It means even after pi T1 will keep on conducting, but we know that after pi supply voltage become negative. So this is negative now, this is 0 now. Which one is lowest? This point is lowest. So now you can say that D2 and T1 are conducting. So during this interval T1 and D2 are conducting, because T2 is not fired. So you can say that T1 and D2 are conducting. If T1 and D2 are conducting, it is sorted here, so the current is freewheeling. Current is freewheeling, so the output voltage is 0. Okay. Now at this instant again T2 will get fired. So T2 get fires. T2 get fired. Okay. So if T2 is fired, then T1 will be turned off. It will be reverse bias. So now since VST is negative, in these two devices D2 will conduct and above T2 is conducting. Now D2, T2 are conducting. Now D2, T2 are conducting. If D2, T2 are conducting, then the output voltage will be negative of this supply voltage. So negative of the supply voltage is this. So you can say that this will be my wave shape of output voltage. So this will be the wave shape of output voltage. Now you can calculate the average output voltage. Whenever there is a freewheeling action, remember output voltage will never be negative. Output voltage can never be negative since it has inbuilt freewheeling action. That's why output voltage can never be negative. Okay. Now this will be the output voltage. You can calculate the average output voltage. What is the average output voltage? 1 over pi. The period is pi, from alpha to pi, Vm sin omega t d omega t. Okay. And you can calculate the average output voltage from here. Vm by pi. Integration of sine is minus cos upper limit minus lower limit. This will be my average output voltage. And you can see that for whatever value of alpha you take, it will always remain positive. Average value will always remain positive. It will never be negative. Okay. So this was about semiconverter. There is one more type of semiconverter. Here you replace both the diodes and here you replace with both the transistor, both the thyristors. Okay. So this way also you can solve. This is your homework. I mean, do it yourself. That both in one leg we have diodes and in one leg we have thyristor. You can do it yourself. Okay. So this was all about phase control, single phase control rectifier. I hope you enjoyed because this class was crisp and I have told you everything, almost everything about this phase control rectifier. So single phase control rectifier. Okay. I hope you enjoyed this session and let me give you some questions, guys. Let me give you some homework. Okay. Let me design some question. Let me give you some homework. Please do it. Okay. Let's say I have this circuit. This is R, this is L, and this is E. Okay, this is R, this is L, this is E. This is 10 ohm, 0.05 Henry, and this is E. The firing angle alpha is given as 60 degree. Find E max. Find E max such that conduction remain continuous. Such that conduction remains continuous. Such that conduction remain continuous. And it is given that omega L by R is equal to omega L by R is equal to 2. It is given that omega L by R is 2. Okay. It is provided to you. We need to calculate what is the maximum value of E such that the conduction remain continuous. Alpha is already provided to you. Alpha is 60 degree. We need to calculate for what value of E the conduction will remain continuous. What is the maximum value of E for which the conduction remain continuous? Okay. You try to solve this question. Again, it's very good question, guys. How to solve it? If you remember this condition, then theta z is tan inverse omega L by R. It means tan inverse 2, you can calculate, okay? And this alpha JC is given as 60 degree. We assume that for alpha equal to 60 degree, conduction is just continuous. In the worst case, you assume that the alpha equal to 60 degree, the conduction is just continuous, okay? So you put alpha JC equal to 60 here, okay? And theta z tan inverse 2, and only E is unknown. You can calculate this Z also, na? This Z also you can calculate, and everything you can calculate. You just put it here and you will calculate the value of E. I think it's easy peasy. Now, let me give you one more question, part 2. Part 2. If E is reversed, if polarity of E is reversed, if the polarity of E is reversed, find power delivered by the load, find the power delivered by the load if alpha is equal to 98 degree. If alpha equal to 98 degree, find the average power delivered by the load. It means this load side will deliver the power. If the polarity of E is reversed, and if alpha is 98 degree, because alpha is greater than 90 now, okay, alpha is greater than 90 now, so we have to first calculate the value of E. The this E is used, okay. For this value of E, if I reverse the polarity of this E, find the average power delivered by the load. How much power is delivered back? We need to calculate, and alpha is given as 98 degree, okay. Alpha is given as 98 degree. So there are two questions, you need to solve it, and please comment in the comment section, okay. So I'll reply you in the comment section if you solve it, okay. So that's all for today's session, guys. I hope you enjoyed, and I hope you enjoyed this single phase controlled rectifiers, okay. In the next session, let me tell you on which topic I am taking the class in the next session. In the next session, I'll take the class on, wait a minute, yes, 3-phase voltage source inverter, okay. So I'll take a class on 3-phase voltage source inverter in the next class will be on tomorrow, and it will be on 3-phase voltage source inverter, okay. So that's all for today's session, guys. I hope you enjoyed, and please revise today's session. If you don't know anything, let's say some points are missing, if you don't know anything, or if you have not studied any point, because it's not necessary that you have studied from me only. So it might be possible that you have studied power electrons from some other faculty. There is no problem. If you have not studied from me, and if you have problem with some point, let's say if you have not understood any point, okay, so please reach to me. You can message me in the chat section, or you can join my Telegram link. You can join my Telegram group. The link is given in the description. So you can join that Telegram channel, and you can comment over there, and or you can directly ask me. If you have my number, you can WhatsApp me, you can ask me, okay. So that's all for today's session, guys, and thank you for showing interest in this class. Please do subscribe our channel if you have not subscribed it, and like the session. And this is the link of you can say the link is provided in the link is provided for mobile app, okay. So you can join that that mobile app, and you can install that. Go to the Google Play Store, and then you can install that app. On that app also, you'll find some free sessions on all the subjects. Every faculty is teaching you, so you can join those sessions also. And that's all for today's session, guys. See you in the next session. Thank you and take care. Bye.